you going? I say, okay, Rome. Which region of Italy? And say, look, it's Rome. I mean, if you don't know, it's your, you know, whatever. So this drives, is the first time I feel it myself, because usually I get so angry that my wife feels it for me, because she's afraid I'm going to hurt myself or break the computer or something. So this time I did it myself, and it took forever. But anyway. Huh?
Did you hurt yourself?
No, but I was actually really getting angry. Yes.
Do we have to do anything for the all setup? All setup is basically streaming live already. Cool. Very good.
Okay.
To what? To YouTube.
YouTube.
Yeah. So we. People don't know. They should send it out. It's in the email. Exactly. Okay.
Actually, even told you it said so in the email.
Anyway, so I'm really extremely happy that we have as our last event in this year the fantastic special occasion to welcome GIORGIO GRATTA from Stanford here in Vienna again. It's really nice. So I really hope that we continue regular visits of you here to Vienna to continue and increase the exchange. So Giorgio has an interesting background in high energy physics. So if you look what Giorgio has been working on, it's neutrino oscillations and other things. I think as deep as QCD, even in the early young days, I guess. And he moved after his PhD in Italy, in Rome. He moved to the US. He had some Italian fellowship and working at SLAC, so continuing the high energy physics direction. He was then a postdoc fellow at Caltech, but working in CERN. So we discussed this yesterday. So basically, you were employed by Caltech, but he worked at CERN. And then eventually he got a faculty position at Stanford, where he stayed ever since. Giorgio is, I said that already, interested in many things. He, of course, continues also his interest in high energy physics and in particular fundamental interactions, and this has led to a series of wonderful tabletop experiments, part of which he's going to tell us about today. Giorgio,
okay.
Thanks a lot.
Thank you very much. Thank you. And thanks for having me. It was really good to actually come to Lorenzo's defense, which was, of course, until the last minute in doubt. Not the defense, but the coming. And so anyway, so I'm really glad I'm here. When Marcus asked me to give a talk, I was a little bit reluctant because, you know, I gave a talk actually. One of my last trips overseas before the pandemic was actually in Vienna. In fact, you gave the last colloquium, I think, in person at Stanford, and then you managed to slip out of the country before everything got shut down. And so, but anyway, and so I was not sure. I had many new things to tell you about, at least in this area for my group. But then, you know, finally, our paper appeared today on the archive, so I'm free to actually tell you about the latest thing. So that seemed kind of a reasonable thing to do. Okay, so since I gave the first part of this talk, well, I mean, I gave a talk on a number of things with our microspheres 2 years ago here. I will just summarize things briefly and then talk about, you know, this is part 2, the pandemic years. All right, so that's actually what I'm going to do. I say I'll just summarize the initial part and then talk about the first gravity measurement around 40, well, I should be a little bit careful. The first measurement relevant for new forces at short distance with sensitivity around 20 microns. And then the most recent thing, a new technique to actually measure and reject, and I say all in quotes, but many electromagnetic backgrounds. So you'll see that those two things come together nicely because I'll show you that the first gravity measurement, or this first measurement here, is actually limited by primarily by electromagnetic backgrounds. And so it's a good segue to say that as we are upgrading our trap, we found a way of suppressing many electromagnetic backgrounds at least. So we're really quite excited for the next run. Okay, so in the way of introduction, this is our knowledge of long-range interactions, gravity-like interactions as a function of lambda, the scale at which the interaction is sort of active, and the strength of the interaction. And I really like this plot because it spans many different, very many different techniques and orders of magnitude, both in the vertical scale and in the horizontal scale. The horizontal scale here is in meters, but you see here is in astronomical units, goes all the way up to the boundary of the solar system. And you can see that the best knowledge comes from lunar ranging, where we know the position of the moon at any given time to about a centimeter or something, which is really surprising. It is done by laser ranging. And there's lots of physics here having to do with how you measure it at geophysical distance or with artificial satellites. But we are interested for this talk about this very left corner where measurements are done in the lab. This kind of bottom here, or this minimum here, where there's most sensitivity around this region, is at a distance of about 10 centimeters or a centimeter. So this is the classical torsion balance kind of experiment. But we are interested in even further to the left here in the sub-millimeter region. Okay. All right, so let me not spend much time to say why this is interesting, because I think you all know that. So I'll just move on to experimental challenges and why this is hard. And again, I think you probably all of you know this, but it's sort of the last two items here are kind of interesting. I want to spend a little bit of time on them. So, okay, the experiment is different primarily because the force you're measuring is very small. This is the force. And when you plug in the masses and you actually put in the density, you're stuck with density of terrestrial objects. And the volume of the objects is essentially the cube of the size of the objects, because of course if you make a measurement at 10 microns and the objects are like a meter size, the 10 micron doesn't mean anything because they're very far away just because of their size. So essentially you're stuck with the fact that the force goes with g, which is a small number, the density squared, and then the radius to the fourth power, or the size of the object to the fourth power. And so as you go closer and closer, and the radius becomes smaller and smaller, the force becomes really very small. And at 10 micron distance, you get this equation here gives you about 10 to the minus 21 newtons, which is the kind of force you have to measure. Equally important, and in this moment even more important, is the fact that at distances of, let's say, less than a tenth of a millimeter, even neutral objects actually have electromagnetic interactions through essentially polarization effects of various sorts that we'll discuss more in a minute. And so this is a dangerous background when you go to shorter and shorter distances. In fact, if you go below maybe a micron or a fraction of a micron, I think it becomes impossible to do measurement, to do meaningful measurements this way. And if ask me later in the questions about this, because there is a new thrust of research that we have started on this, but I don't have time to actually put it in the main part of the talk. That's a different technique. But so this is really interesting to try to figure out how to beat down this background. And related to this, there is this last point, which may seem a little bit critical of some earlier measurements, but it's reality, and that is that the experiment really should have discovery potential, not just the ability of putting limits. And that is to say, one has to be reasonably sure of or understand backgrounds well enough and to have a model of the background, and so that you can tell whether the signal you're seeing is a background, is just the background or something new. And essentially, virtually all experiments in this area, including our first measurement, essentially just say, well, okay, so I see a background. It doesn't look like the real thing really, but I'll just put a limit at the level of the background because I don't know how to do otherwise, okay? But that means that if there is a signal in there, you'll not see it. So that this experiment can set a limit, and it's a valid limit, but has no discovery potential, okay? And so the idea of identifying the background is to try to improve this situation. I don't say fix it because this is really hard, but actually to move closer to a background-free experiment. And just to give you an idea, I should actually have put a plot on this now for next talk. I'll do this. In my other life, say searching for neutrinoless double beta decay, which is something where also backgrounds are very important, but we model the background extremely well, and there's all sorts of ways of checking that the background where you need it is very small or a certain size because of something else that happens elsewhere. There's lots of gamma ray lines, and you measure all the gamma ray lines with very high intensity, and then you just look at the same, you extend the same spectrum to the region of energy you care about, and now you know extremely well what that background is, even if there is a background. And so you can subtract it because you know it with very good sort of sensitivity. I mean, you know the background really well. So the idea would be to move closer to that sort of situation. All right. So the main topic or part of the discussion today has to do with an optical trap, which is similar to the kind of things, of course, you have here, except I guess the most important difference maybe is that, forget about all these things, it's just too much text here, but is actually two kind of things. First of all, we try to have a very good Gaussian mode for the trapping laser, and the reason is that we want to get very close to the trap microsphere with what we call the attractor, which is essentially the thing that produces the new force. And so we want to have as little beam tails as possible so that we can actually not disturb the beam or the trap as we get close to it. And then the other, and so for instance, we used to have a trap using lenses to make the final focus of this thing, and now we use parabolic mirrors because there's only one optical surface, and you don't get shadow beams or halos and this kind of thing, so you get less of that. And so there's a number of things that are actually done very carefully with this, for this. The other thing which is important here, which you'll see a better picture of later, is that the trapping region is essentially made by a little cube of 6 metallic sides, which are actually like conical things, so the trapping beam goes through it, which you can sort of see here. But the little microsphere is a little cavity made by those 6 facets of metal, and the 6 facets can be biased in a totally independent way, one from the other. And so there's a number of things having to do with electrostatic backgrounds that are actually somehow dealt with in that way. Okay, so that's actually, sorry, that was a better picture. And that's actually a rough schematic of the optics, some sort of a simplified schematic. But what we do is that, and you probably remember this from last time, at least the ones who were here 2 years ago, that we actually image the position of the microsphere in the horizontal plane by the light coming out. That goes onto a position-sensitive into a quadrat photodiode here. And it's done also interferometrically. This is actually, there is a wavefront coming in from the trapping laser that is recombined here. So the QPD really gets interferogram, and if there are paths of light, this is actually to suppress somewhat halos. The back-reflected light, and you guys used it, I heard it yesterday from Lorenzo, is actually used to actually measure the vertical position of the microsphere, again, interferometrically. And then the other channel in this thing is that the trapping laser is polarized linearly in one direction, and since the microsphere is slightly birefringent, we actually extract also the opposite polarization here, which goes just in a regular photodiode, and that is to measure the spinning of the microsphere, which becomes important later. This is all done with great care to actually try to have everything stable, so it's mounted on a granite table that is on active suspension and all this kind of stuff. The vacuum chamber now is very large compared to the old one because there's lots of actuators inside, so you need room for actually installing all these things. You can see here the cube, the external part of the cube, and the cones, or that go in through which the laser beam goes sort of up, and then this is actually the attractor coming in on a high bandwidth positioning stage. This is the stage that scans the attractor sort of back and forth, among other things. All right, so now a few results from the past, which I've shown already, just to set the stage of things. the first thing you have to do, as you well know, is to actually discharge the microspheres. And we've learned to play lots of games with those things. You can see here the quantization of the electric charge is completely obvious and have huge signal-to-noise ratio. These are two charges, one charge, 0, and then you can actually go the other direction. The 0 part, you can expand the vertical scale by increasing the bias, the amplitude of the field that actually oscillate the microsphere. And then you can see here the data that is actually really quite clean. The scale here is 10 to the minus 3 of an electron charge, and we'll see later that we are now 10 to the minus 5 or that sort, but you will see this later. And this is done, was done in this old paper by essentially just having two plates, to applying an AC to two of the two opposed facets of that cube, essentially, and that's all there is pretty much. Another thing is, of course, to show that you can bring stuff very close and still have very good noise. Again, this is kind of old data, but it's whatever, it's just the right thing. This is a case where you actually put a very large charge on the microsphere. Sorry, our microspheres, by the way, are either 5 or 7.5 micron diameter. Much of what I show later is 7.5 micron diameter. This data here is 5 micron. But anyway, they behave very similarly. And so you can see now this is the noise as you have the very charged microsphere, and you actually bring a neutral, a grounded beam. See here, it says silicon, but in fact it's gold-plated, so essentially it's like gold from this electrostatic point of view. And so when you scan this thing, you scan the relative position of the microsphere in the trap and the beam, and you can see that you go down to less than 20 micron distance. In fact, this was actually 15 micron, the closest approach. And what you see here is actually the noise, the little vector shows the direction of the noise and the intensity, the RMS of the noise for the sphere at different planes in this way, because you're really measuring a vector field in 3 dimensions. So there is lots of information. You cannot put all the information in the same plot, right? So this is essentially x versus z, and then the forces the vectors are fz and fx, and the different colors are different y slices of this coming out of the board. Okay, but this is just to say that you can actually, and you have noise RMS of the order of 10 attonewton for those relatively large spheres. The system is very linear. You can change, you can actually now bias the attractor, and you actually measure the force, the 3-dimensional vector of the force very well. So this is essentially like AFM, which is fully 3-dimensional. And respect to AFM, you cannot go as close as AFM, at least not yet. But you're fully 3-dimensional, and you measure, and as the sensitivity, a force sensitivity which is close to cryogenic AFM, or actually maybe a little bit better than cryogenic AFM. So you can scan surfaces with these things. Another thing that is required in order for for the rest of the talk to proceed, or for the rest of the work to proceed, is actually characterizing microspheres in the beam itself or in the trap itself. And now, ideally, what you would like to do is to put a charge on the microsphere and then turn off the laser and see how much bias you need to suspend the microsphere up. But you cannot do that because you need the stability, you need the laser to actually have a stable trap in there. But what you can do is to actually bias, put some charge on the microsphere, bias the upper and lower electrodes to either help gravity or counter gravity, essentially, of the Earth, and then you see what power the feedback, how much the laser power changes to maintain the microsphere up there. And this is, and so then what you do is that you actually extrapolate this down to 0 optical power, and when you do that, you actually, then you know what kind of electrostatic force will be countering gravity, and therefore what is the weight of the microsphere, and so what the mass of the microsphere is. Again, you cannot do this, so you could also say, well, but you have the radiation pressure, just measure the radiation pressure because you know how much power the laser has and so on. But that's very hard because you have to calculate the overlap integral between your beam and the microsphere and all this, and so on. So that's, not easy to do, and in fact wouldn't give a good result. So this technique actually works really well because you're only measuring relative power. You only need relative power to actually do this, so you can easily measure it with a photodiode. So you actually get very consistent results. So this is the mass in picograms of, these are the 5-micron diameter microspheres measured in different runs with different microspheres. With the same microsphere but different runs, and especially, these are different microspheres. Each vertical slice here is a different microsphere. And each microsphere gets 3 different measurements done with positive charge on it, negative charge on it, good vacuum, less good vacuum. Essentially, those are the 3 markers. Don't ask me which one is which because I don't remember, but it's written somewhere. They're all consistent with each other, so now they get averaged, and so now you have 1 point per microsphere here. The last 3 microspheres were cleverly recovered after the measurement by just turning off the laser, biasing things, pulsing something, and dropping them on a piece of silicon that is nearby. And you can see them here. They're Mr. 1, 2, and 3, which is actually surprising you can do this. But if you get the right student and he knows how to do it, I certainly couldn't do this. But at the last minute, you just do certain things, and the microsphere jumps on there. So now you can put this in an electron microscope and measure the diameter very carefully. And you get those diameters here. You can see, sorry, this is the radius, so it's 2.35, whatever, microns. And you can see that the 3 microspheres from the same batch are very, very similar to each other. Also, you can take a large amount of microspheres, which of course you haven't now weighted in your trap, but they are just part of what you bought from the manufacturer, and actually then measure, use software to actually measure the radii from an electron microscope picture, and so so our 3 special microspheres are very well in agreement with the average, with this distribution of diameters or radii of all the microspheres. And this is also, when you put in the electron microscope, it's never clear whether you should really coat them or not coat them, because if you don't coat them, they're glass, so in principle maybe they repel the electrons, so you get slightly different diameters. But you see that the distribution in the 2 cases is very small. It is very, very similar. The difference is very small. So we know the radii of these things really well. So that means we can extract the density of those things, which is actually surprisingly quite a bit lower than the fused silica density, which is supposed to be 2.2 grams per cubic centimeter. So presumably those things are kind of porous, or they have some sort of funny, kind of fuzzy shape, which is not surprising, but also may mean that, when you think about polarization of them, using directly the numbers of fused silica may not be the right thing to do, and there might be other effects that one has to be somewhat careful about. So I told you that about spinning, and so this is actually the simplified part of that part of optics. So you have linearly polarized light coming in from here, and then now in this particular case, I'm looking from top, and I have the 4 electrodes around that have applied 2 sine waves 90 degrees out of phase. So you get an electric field spinning this way, as is shown down here. And so now the microsphere has an electric dipole moment. And so it gets dragged around, and there's a torque applied to it. And if you ramp it up slowly, you can essentially lock it and drag it, and pull it up in spinning frequency, essentially. Okay. Now, since the microsphere is also slightly birefringent, it's really convenient now because you excite the rotation electrically and you detect it optically. Which is also kind of electrically, but anyway, it's a different frequency. So you detect it optically, and that's sort of convenient because you don't mix those things up. This trap, actually, this is the old trap with lenses instead of the mirrors, but that's the same thing. Okay, so, and of course you can, I'm showing, all the data I show you is always assumes that the microsphere is rotating in the horizontal plane, but in fact, at the end, the data that we have actually for this electrostatic cancellation and so on is done by trying to rotate in each of the 3 planes, and it works equally well in each of the 3 planes. So we'll actually get to that later. Okay, so when you rotate, when you actually rotate this thing, what is the signal? Does the signal look like? Well, you see the rotation, actually 2 times the rotation frequency, of course, because you're reading out with polarization, with linear polarization, so you actually see at 2f the signal here, and then there are side bands. Side bands are due to the fact that the microsphere, the electric field goes around. If you go in the reference frame of the electric field, the microsphere does this kind of thing. So you can actually use this in a minute. This is the libration of the microsphere, which we'll discuss later. If you stop driving the microsphere slowly spins down with a certain time constant that depends on the pressure in the vacuum chamber. In fact, well, we'll get that in a minute. The reason, the way to confirm that indeed that is the libration, that feature is the libration, you can increase the strength of the electric field that you use to rotate, that rotates around the microsphere, and you find the right relationship between, and so as you increase the strength of the field, the thing goes faster, oscillates faster around the direction of the electric field, which is shown here, and it works with the model really well. Once you fit this thing, you can actually use this to measure the ratio between the dipole moment and the moment of inertia of the microsphere, of course, which we'll use later. And if you use the moment of inertia, if you use the previous measurement of the density and you assume it's uniform density for the microsphere, now you can extract the dipole moment, which for this particular microsphere is 127 electron micron. Later on, we'll see, by now we know much more about this. This is just one particular microsphere, but we'll get to the rest later.
So,
yes.
Back 2 slides.
Oh, 2 slides. Yes.
So it's now electrically spun up.
Mm-hmm. Yeah.
You have a charge on there.
No. Sorry. This is a neutral microsphere. This has been neutralized. There's just the dipole moment.
Okay.
Yes.
Neutralized.
Yes.
And then you spin it up.
Yes.
With a time-varying electric field?
Yes, I mean you have essentially a sine wave electric field with 2 sine waves 90 degrees apart applied to 2 sets of opposite electrodes.
Right, and then you have an additional DC bias?
There's no DC bias in this data. We'll get to the DC bias later. That's a good, but just hold on because that's for later.
Okay.
No DC bias in this. Okay. So, all right, so actually there is another way. So I can actually measure the vacuum in the vacuum chamber by looking at the spin down. Or there is another technique that is what I can do is that as I change the pressure in the vacuum chamber, which is actually the horizontal axis here in millibar, which refers to everything, right? It's all the same. You see that at some point, the phase between the electric field that is dragging the microsphere around and the axis of the microsphere increases, essentially because there is viscosity of the gas that applies a torque to the microsphere. So I need more torque to drag it, and so the angle becomes larger and larger. Until the angle becomes pi over 2, that is 0.5 here, and then at that point the microsphere unlocks. You lose lock with the electric field, and then it starts tumbling at some sort of with a random phase with the electric field. So this unlocking pressure, or this once you get to once the thing unlocks, you are measuring the pressure if you want, because this point here is the unlocking position is actually a function of the pressure. And of course you can change the volt depending on the field strength that you're using to drag it around. This unlocking happens at a different place. But if you know this field strength, you can actually use this to measure the pressure again. And so you can see it here. The field. This is actually now the field strength on the vertical axis versus the unlocking pressure. And so again, you can use this to actually make a measurement of pressure. In fact, actually, this thing is sensitive to not just the pressure, but the pressure and the gas species. So if you know the pressure in a different way, you can actually measure this. You can use this to measure the gas species. So this is a little bit like an RGA. except it doesn't measure, only measures the average gas species in there, the average mass of the gas molecules, so it doesn't really do the analysis like the RGA. But on the other hand, there's no ionization. There is some advantages, but the RGA usually requires to ionize the gas, and this thing doesn't. So it's kind of a more gentle thing, and it's much more expensive than an RGA. But you can see it works for all sorts of gases. So the curve is a fit to the data with just one free parameter, this K parameter here. And so it really fits all the data, including exotic things like sulfur hexafluoride or xenon, all the way down to hydrogen here. So that's kind of a cute vacuum application. Of course, those are gyroscopes. They essentially behave like gyroscopes, and you can, once they're spinning, you can now apply a kick in the other direction through a rotating field this way, and now it starts processing like you expected, and it behaves like you expected, and so on. All right, good. That's old stuff. So now we get to the new data. So the first thing is to say, okay, now we can actually start really measuring gravity. And so there's a first measurement. And again, sorry, I say gravity. That's kind of a short form file. You can make a first search for new long-range forces at micron scale. That's actually the way I should say it. Whenever I say gravity, I mean that for the next 10 minutes or something. And so the way it works is that there is now the microsphere in the trap that you see here. This is now one of the 7.5 micron diameter spheres. So we're talking about slightly larger spheres than what I showed previously. The attractor is essentially a patterned silicon beam where some of the silicon is being removed and replaced with gold. And I'll show you much more about this later. There is an electrostatic shield that is not moving in front. It looks like sort of something like a corner piece like this. And that's it. So now you actually leave the shield steady, move the attractor back and forth this way, and see what kind of effect you get on the microsphere. Notice that unlike previous measurements of this kind with torsion balances, or even to a large extent the ones with cantilevers like Aaron Kapitulnik measurement in also at Stanford, this thing is fully three-dimensional, and there are a number of interesting features to the signal that we haven't used yet in the data I'm going to show you. In particular, if I position the microsphere a little below or above the plane of the attractor, I really get all three forces, or the contrast in mass or in density gives me three forces: one vertical, one this way, and one this way. And the one, the vertical force and the force towards the attractor are in phase, and the force along the attractor is 90 degrees out of phase, because as the heavy and light fingers are transiting in front of the microsphere, you get pulled this way, but it's 90 degrees out of phase. So all of this stuff is actually going to be useful to actually identify the force you care about against some of the backgrounds. However, in the present system, the noise in X and Y is much larger than the noise in Z, so I'll only use the Z data. If I could use the other data, but it's so much noisier that it makes no difference in the end in the result. And this is going to be fixed, but for the time being there is that issue. The separation.
Sorry,
yes.
Move along Y.
I move, yeah, those are my axes. It's always difficult to remember. I don't remember myself. But the only obvious one is Z. But anyway, you move along Y, and the primary force, in a sense, is along X. The force you think about usually is along X, but you get forces along all three axes. The separation is about 15, 14 microns. And you see we're running with a Z offset exactly because Z is the better axis for us to do the measurement, and so we offset it because otherwise we wouldn't have a good measurement, essentially.
Because if the separation, Z separation would be 0, you wouldn't get a signal.
If the Z separation is 0, then you don't get a signal in Z, exactly. And eventually, once everything works really well, we're going to scan all these things, right? And so you really constrain the signal this way. For the time being, this is one of the things that just barely works. So you just just do with whatever you can. This is the way this thing looks like. Actually, this is a little bit of a lie. This is the old trap, but the new trap looks very similar, and it's kind of a nice cartoon. So All right, so you can see the cantilever sticking out of one of those holes. So you can see actually here the 5 of the 6 facets or cones, which are pyramids on the outside and cones on the inside. The top and bottom ones are used for the laser beam to go through. And then we use this thing for, one of those holes for the attractor that comes in. You can see a detail of it here. It's 10 microns thick. The shield comes in from 90 degrees apart in front this way with another actuator. Okay, and that's pretty much it. And then this hole here is used for metrology. There is a microscope that looks sideways to actually measure the relative position of everything, essentially. And this is a picture taken in the old trap, taken from top, just showing a microsphere where the surface of the microsphere is about 5 microns away from the surface of an attractor, just for fun. That's actually the fabricated attractor device. There is a silicon handle that is quite thick, and then the cantilever sticking out is only 10 micron thin. And you can see the gold and silicon sort of fingers. This is done before the entire thing is coated with gold, because afterwards you don't see anything. But the real thing is coated with gold before you use it. And you can see here the scale of things. The size of each of the fingers is 25 microns, so the center-to-center distance is 25 microns, and the thickness, as I said, is 10 microns. The shield is kind of interesting. It's also microfabricated in silicon, and there is essentially a slot through which the laser beam goes, and the attractor is hidden behind this thing. Actually, we both have the ones that are solid on this side and sculptured on this side, and the ones like the one I'm showing here that has the same kind of structure on both sides. They're just interchangeable, essentially.
Sorry.
Yes.
So the thickness, go back one. You just say the thickness was 25 microns. It looks much.
This is 25 microns.
So the thickness.
Oh, the thickness is 10.
10 microns.
Yeah, I mean, this image, you can see smaller, whether it's exactly, it is exactly 10. This has been measured with metrology to be 10, but it's approximately, you can think of it as half of the size of the finger or something like that. Okay, so one thing, of course, you want to do is to put a charge on it. I mean, compared to some of the other measurements, the beauty of this thing, one of the beauties of this thing is that it's absolutely calibrated. You put a charge on the microsphere and, excite the 3 degrees of freedom and see what kind of response you get. And in fact, you get the diagonal. So this is exciting X and reading out X, Y, and Z. And then you get the off-diagonal elements. This gives you an idea of how much crosstalk you have between degrees of freedom, which is non-zero, and it's order 10%. And this has to do with things we don't fully understand, but in particular, if you have a small misalignment between the cube, you think that the cube is vertical and the laser beam is vertical and so on, but this is never exactly the case. And maybe the beam is not exactly centered in the cube system and so on. So this is essentially measuring the overall misalignment between the electrical reference frame and the optical reference frame, which are, in general, different things. And that's just a movie that is actually slowed down. I mean, the real frequency we run this thing is about, the main frequency is 13 hertz, actually, so it goes somewhat faster than this. It's very hard, but you can see the slot in the shield, and the shield itself is this thing, and the attractor. This is done from a second microscope we have that looks from the top, but this looks through the parabolic mirror, and for the time being, we're not smart enough in ray optics, so that's not corrected. So it's got lots of, I don't know, it's called pincushion aberrations or something. So in the very middle of the image is a good image, but as you move away from that, you get those kind of funny distortions and so on. The side microscope is a good microscope, but this thing is kind of, it's nice to actually look at things, but it's not, very good at metrology, sort of. Okay, so what you see in the run. So what you see is that, so this is the force, and this is the z-axis, I say. I don't even show you the x and y axis because they're much worse, actually. This is the frequency, and you see, so our excitation is at 13 hertz, which is somewhere here, is this thing here. And so the blue little lines is from the simulation what you expect from a monopole force excited in this way with all the harmonics. And then, let's see, and then the black is the spectrum you get if you're not moving the attractor, and the red is the spectrum you get if you move the attractor. So two observations. First of all, the continuum background essentially doesn't change whether or not you move the attractor. That's good, sort of. There are probably some vibrations in the system that we don't fully, in fact, actually, let me tell you one thing which is kind of funny, that this is all happening in the lab. I'm sure Marcus is more hands-on, so he goes to the lab more often. But I actually, I don't know, I didn't go to the lab for a couple of weeks maybe or something, shame. And so then or maybe I went to the lab, but things were not working or whatever. So one day they were taking data, and I'm going there, and there's this thing, and from a window you can see this thing, this goes, say, wow, that looks pretty violent. So are you sure nothing vibrates in there or something? I mean, this is just pretty, it feels pretty intense. It's light, but it's maybe 50 grams, and 50 grams moving at 13 hertz start being kind of an exciting kind of thing. So we have some vibration on the optics, and in particular, the one reason why Z is better than X and Y is that the top parabolic mirror was probably not rigid enough, and so there's some vibration in the imaging system caused by this thing going back and forth, rastering back and forth. But still, you can see that this is actually pretty good. There are some lines, but you see the important thing is that the lines you see have nothing to do with the pattern that you expect from your new force. That is the relative intensity. So for instance, okay, this line is actually this line here is something that we always have in the data. We don't know what it is, but you see that there is either you move or not move, it doesn't matter. Same as this, but this is clear what it is because this is half of 60 hertz. So that probably comes from the line frequency. But then, okay, so now I'm going to have trouble. Yeah, so for instance, you expect stuff here, and there's absolutely nothing. And you expect something here, but this is very low, whereas you get a very strong line below, like at 9 hertz, which should be almost nothing. So the pattern doesn't make sense. There's no real, it doesn't follow the right harmonic pattern that you would expect. And so now what you can do, again, this is the Z channel only, you actually you take the 6 highest harmonics. And, some of my postdocs come from particle physics, so they're very much into statistics and doing this thing like, blind analysis and all this, so it's done very carefully in a sense, at least. That is, you decide the 6 strongest harmonic just using the simulation, just don't look at the data, but just take the 6 highest of those things and use those, and then simultaneously fit all of those. So those happen to be 12, 18, 21, 33, 36, and 39 hertz, where you expect to have the most signal. And this is over a run, which is about 24 hours. First of all, you can see that there is a trend where somehow the signal strength goes up a little bit. Clearly, the new forest shouldn't change over a day just because you're doing your experiment. So there is also this pattern that you want to have sort of temporal stability of your signal. And then what you see, you compare, you build some sort of likelihood function that essentially tells you how that pattern of harmonic looks like, how similar that is to what you expect. These are the systematic effects that are estimated for the measurement. For instance, you see that there is very small uncertainty deriving from the position in X and Y, of course, but since you're doing, between X and Y, Y and Z, but X is measured less well because can only be measured from the top microscope, which has all the aberrations, so you get this 30% uncertainty from X, and then there are other uncertainties from the microsphere weight, which is small, but and you can actually look at all this thing. It doesn't really matter what this is. All right. So then the question is, what is there is some stuff happens, doesn't have the right pattern, but again you are in this situation where so you can say, okay, so I'll set a limit at that level, but it would be nice to understand the background a little bit better. And so there is actually, maybe this is too complicated, too many lines, but these are the expected X and Z forces at many frequencies of, around what you care about, due to essentially a dipole interaction of the microsphere with the attractor itself. And so now there is actually two things that one has to, for a long time, we were concerned about patch potentials. The attractor is all coated with gold, but of course that doesn't mean it's equipotential at the level of 100 micron, 50 millivolt or 100 millivolt. It turns out that once you are behind the shield, that doesn't really matter. You can simulate this, FEA, and it doesn't really matter because the attractor is essentially hiding all those kind of granularity of electric field. However, what still happens is that, and maybe I can actually use the whiteboard here, what happens is that if this is your shield that is protecting this part, and you have the attractor swinging back and forth behind the shield, there is some fringe field coming out, or maybe going like this or something, because this is, because this is grounded, and this thing here is also grounded, but there is some contact potentials between the two of them, which may be different. And so you get essentially electric fields doing this, and some of them leak out, and they produce gradients here. And as this thing moves back and forth, you change how much of this there is that the microsphere is exposed to. So that is actually the main, and that's what's, and so here we're with FEA, you're calculating those kind of harmonics and see essentially what you see. And you actually see something which is consistent with a contact potential of about 50 millivolts, which is entirely plausible, let's put it this way. Okay? All right. So there's other backgrounds that we know exist, and to some extent we have tested. One is stray light, and that is due to the fact that the attractor and the shield are not black, first of all, because they're so delicate that we don't know how to coat them black, and so they're gold coated, and so they are somewhat reflective. And if there is a little bit of light in the chamber, it hits the attractor, and then it gets imaged by the imaging system. Now, the imaging system has interferometry, it's supposed to suppress light coming from places which is not the microsphere, but this only works to some extent. The Z degree of freedom works better for because of what I told you before, but also because the shield really hides the attractor. The attractor, from the point of view looking from behind, is really behind the shield itself. And so the moving attractor doesn't get imaged into the backscatter interferometer, whereas to some extent, if there are some halos, is imaged into the X and Y degree of freedom. So stray light is a problem, and to be honest with you, this is really hard, and we were not particularly careful. We were somewhat careful, but not particularly careful. And so we've discovered afterwards, you go there with an infrared viewer and you see all sorts of halos, and you take a picture with an infrared camera and you see all sorts of halos of light bouncing around and so on. So we need to be more careful. And in fact, we talked a lot with LIGO people about this. And in LIGO, there are people who do nothing else but looking at halos. And it's a very, and they have actually techniques that we learned from them to actually reduce this. And so this is being done now to the trap. I told you of vibrations induced by a attractor. And then finally, there is laser pointing noise and then Casimir forces. But those are at this point very much subdominant. And so electrostatic, stray light, and vibrations are the most important things. All right. So anyway, so you can actually do that fit. And we don't use the background model, so because we don't understand well enough the background to subtract anything. So we just don't subtract anything, which means our limit is this thing here, which is not particularly, it's not better than some of the others. However, I would like to really point out that some of the others are not as carefully done. In particular, this measurement here, which is published, so it's here because it's published, This is crazy. I mean, they have a huge background, and they essentially say, well, but that's background, I subtract it. And then they essentially have a limit which comes just from the noise of the measurement. But, this is kind of, okay? So this definitely has no discovery potential. It could very well be that there is a new interaction between here and here, and they haven't seen it because they just do that kind of silly thing. So I think the Washington measurements are very carefully done. And this is there is different quality in some of those measurements, but we're getting there. And the idea is that if we were to remove the background, the electrostatic background, we would be here. And if we were to use a 10 micron diameter microsphere, which is very possible, and improve somewhat some of the other issues that we had, we would start eating into new territory, even with those measurements that are not very solid. Okay, so those are the upgrades we have. Stray light, as I told you, the EDM, I'll tell you much more in a minute. The rigidity of the system, particularly the top mirror. And then, actually all the in-air optics that we have, particularly the input side, is in air. There is a box around it, but it's still in air. And I think I want to actually have helium in there. Doing it in vacuum is quite a bit more elaborate, but replacing the air with helium is not that hard. So the upgrade of the trap includes the possibility of actually filling helium. In addition, there's a few other things. We are building, unfortunately, this has been delayed a lot by the fact that we didn't have time to work on this. Instead of having a quadrant photodetector, have a 100 pixel, 10 by 10 pixel photodetector, which is made. The idea being that if you have halos and so on, you can see them. And instead of just taking the centroid position, you have some more knowledge of what kind of light you have there. And the reason why this is kind of delayed is that once you have 100 pixels, you need 100 channel data acquisition system with amplifiers and everything, and somehow there's just too many other things going on. So this is, we have the sensors, but we haven't really used them. And then actually, this is having to do with the vibration. In principle, you can have a rotary attractor. Instead of rastering back and forth, that does this crazy kind of vibration thing, you can have a little wheel. And if you think about it, you need a wheel which is maybe about a millimeter diameter that actually fits into one of those holes in there. And this is not very different from a wristwatch, particularly in the old days, women's wristwatches are just amazingly small. And so actually I had the idea of talking to a friend of mine at the PFL in Lausanne, and they have an engineer who used to work for Rolex. It was great. So actually they built this machine for us that has some gears and then a belt transmission and then a little motor. And the belt transmission is to try to isolate the motor vibration if there are any from everything else. The wheel is not the real wheel for the time being. This has got rubies suspension, like a wristwatch. But the wheel for the time being is just like a uniform wheel, just to test things. And then eventually the idea is to build a patterned wheel with silicon and gold sectors and run this thing. Also, this you can probably run at higher frequency. We would like to run our attractor at higher frequency. The stage can go faster, but then really things start shaking up. And so there is a limit. We'd like to go from the point of view of the noise performance of the system, you want to go higher in frequency, but if you go higher, now you get all this vibration. So maybe this will fix, will solve some of those issues. Okay, but now actually EDM, electric dipole moment. And so the idea is that if you remember my first physics slide had to do with measuring, searching essentially for what at that time we called milli-charge particles, but by now we're much below milli, so those are mini-charge particles. And so particles with a small charge, much less than electron charge, stuck to some of the matter of the microsphere. And I'll tell you later that, in fact, a better interpretation is actually neutrality of matter. That is how close the proton charge and the electron charge are in absolute value. But so that measurement, remember, in fact, again, was background limited, that very first measurement. There was a limit, which was a better limit. It was a better limit than anybody else. But again, the discovery potential was unclear. In fact, we did have a signal those days. And in that paper, there is a mysterious plot with arrows in various dimensions, which is something that people are very confused about. I guess our captions was not good enough, so we got lots of questions about what that plot really means. But that plot showed essentially that each microsphere, when you would oscillate the electric field, it would oscillate also, not in the right direction, so we just interpreted this being, oh, this must be something else. It's not a monopole on the microsphere. It's not a charge on the microsphere. And we guessed that maybe it had to do with dipole moments, but we're not sure. So now this is actually solved to a large extent. So what you do is that now we go back to our system that we said before. Those are the 4 electrodes on the horizontal plane, but this can be done on using any direction. For the time being, I'm describing one possible configuration, but you can do anything you want. So you make the microsphere rotate in the horizontal field, in the horizontal plane. Now the first, and then you apply the excitation field to the vertical plane. So it goes in and out of the whiteboard in this case here. Okay? So the electric field goes back and forth this way, and you look at the movement of the microsphere in this direction while it's spinning sort of this way. Okay? All right. So so at the fundamental frequency of the vertical oscillation of the electric field, you actually get a force, which is EQ for the monopole. And then if there are gradients of the electric field, you actually get the coupling between the electric dipole moment and the gradient of the electric field. This is the term that is more important and we want to investigate better. Of course, if the electric field was infinitely uniform, you would not have to worry about this, but this is never the case, so there is a little bit of discoupling here. And of course, this is the coupling that also produces a problem, with our, that I draw on the whiteboard when you measure gravity, because you get those big gradients that actually mess things up. In the gravity measurement, what I called the gravity measurement before, the microsphere is an unknown spinning state. This was done before we understood all this stuff, so was not, I don't want to say that it was not spinning. We simply didn't know how it was spinning, whether it was spinning, was tumbling around. We don't know that. So the idea is that once you make it spin this way, the electric dipole moment presumably is aligned in the horizontal plane, and so it shouldn't have any effect. The gradients in the vertical plane should not have an effect. Okay? And sure enough, as soon as you do that, the residual background you get in oscillating the electric field in the vertical plane goes down by a factor, at least an order of magnitude. It's more like 50 or something like that. It's almost 2 orders of magnitude, just because it's spinning this way. Now, of course, if there is a quadrupole moment or higher order moment, you can spin this way and still have essentially an effective dipole in the vertical direction. And so that's essentially what we think we're seeing when I say that it attenuates that background by a factor of 50. This 2% left is the fact that the charge is not, that the little microsphere is not just a perfect dipole, but there are higher order moments. In this case here, in addition, there is also induced dipoles, and this is the fact that you are polarizing the material with the electric field. And for the time being, I only have a DC gradient which has to do with contact potentials. This term here for the time being is negligible. So just it's shown just for completeness, but we don't worry about it. So in order to understand this better, the idea is, well, let's just have any gradient we care, but then reverse it into the measurement. Always do 2 measurements with the electric field switched around. And this is actually the sketch. So I've learned yesterday from Lorenzo's presentation that actually it's not bad to have little sketches, and I borrowed Marcus's blackboard to actually draw those yesterday at the last minute. So if you just look at the horizontal plane, the real case has actually 6 electrodes, but just think about, in the vertical plane. Just look at the vertical plane, and so if I ground all the electrodes except for the top one, and the top one is positively charged, then the electric field looks sort of like this. It's very non-homogeneous. This is the center of the trap. And if you have a positive charge, it will be pushed down this way. If you have a dipole oriented this way, it will be sucked up this way. So now suppose I reverse the electric field. Exactly the same thing, but apply plus here and ground everything else. Now you see that the that the electric dipole will be pushed in the same direction as before, but the charge will be pushed in the opposite direction to the one that was here. Okay? All right. So that means that you can build a quantity, that is this A quantity, that essentially cancels out the dipoles and just keeps the QE, sorry, the monopole sort of case. Okay, you know, the monopole interaction. So you see it here. The monopole is still here, but this piece here is canceled, and except there is this omega. Omega is how non-ideal this, what I've drawn here is. In other words, you know, if the center of the trap is slightly misplaced with respect to the center of the electric field, you know, the electrodes, then there is a little correction that you have to apply with that. And you can actually calculate that with FEA, because by now we have mapped, for each measurement, we can map the position of the trap with respect to the 4 electrodes, and so do that, okay? This works wonderfully. I mean, I would have never guessed that this would work so well. Here you can see F plus and F minus. These are the forces in one configuration of the field and the other. And you see that they do all sorts of crazy stuff with time. Sorry, horizontal is time. And this is about 2 days of data taking. And this thing jumps up and down. They walk around and so on. Those are the distributions of those things over time. OK. Now, this A quantity, it's right at 0. And what you see is the noise. This is not. There's no bias effect. There's just the noise. This is centered really well. Okay, so works.
The omega helps in centering. So you can basically, omega is now a fit parameter that gives you the.
Well, actually no. Omega is calculated in this data. Omega is plugged in by using FEA, taking the field map that you get from FEA and calculating omega. Omega, by the way, in the paper, I hope we change it to eta, because I kept complaining that omega looks like a frequency, and it's very confusing because there are all sorts of frequencies. So I hope they did it in the end that it's called eta. But anyway, omega is calculated, is not fit from this. So there's no free parameter here. The center of this distribution is just 0. We'll see later how 0 it is, just out of the box without anything free. Now, actually, there is more information, because you see, those F, if you, instead of doing just F plus minus F minor, F minus or minus omega F minus, whatever, you actually plot F plus versus F minus. Those two lines, in fact, let me just go one more. The blue line is the permanent dipole axis. So a permanent dipole moment appears along this axis here. And the purple line is the monopole. And that's, of course, essentially is F plus minus plus F minus or some other quantity, which is actually a different combination of the two F's, the two F forces. Okay? And so you see that my data, that is this kind of cloud of here, is perfectly centered along the monopole axis, meaning there's no monopole in this data. It's much broader along the dipole axis, because the dipole of this thing moves around God knows how over the time of the measurement. And in fact, it's not centered around 0. This is 0. So there is a little permanent dipole on average in this data. And it's about 20 electron micron, roughly speaking. But this doesn't really mean that much, because you can see it changes with time. And we know that this dipole changes with time. We don't know exactly why, but the dipole changes with time. Maybe charges redistribute on the microsphere over time. Maybe those porous microspheres emit gas as they go, and that changes the charge balance. You know, there's something of this sort going on. But nevertheless, you know now that the monopole, that there's no monopole in this, or there's no monopole interaction in this thing. Okay. Actually, it turns out that there is, you can do more, but we haven't. But this is just, we haven't really done this the homework with data with this for the time being. You know, the induced dipole, on the other hand, if there is an induced dipole, this will appear at 2f at the first harmonic. Actually, do you call this first harmonic or the second harmonic? In the paper, we wrote always second harmonic. Maybe this is the first. This is fundamental, and then the first harmonic. I don't know. This is semantics. It's not very interesting, but
Higher order.
no, but I mean, so the one that is, the one that is the first, I don't know if that's the first or the second. Anyway, some referee will tell us that maybe we used the wrong word. But anyway, at the second harmonic, you can actually build a second quantity that cancels that out. And that is this quantity here, where omega is, again, except omega is squared now, but it's, again, this has to do with this. Is the second harmonic? Okay, so then we wrote it right. Okay. So anyway, and so you can also build a similar system that we had before with this other quantity b instead of a that actually cancels out the term that comes from the polarizability of my microsphere. And so eventually the monopole is a plus 2 times b with this term here. But this stuff for the time being is very small in our trap, and so we don't, we haven't really investigated and we haven't used it yet. Now, as a byproduct, you can extract the quantities which are relevant for the structure of the microsphere. Again, polarizability and how charges move inside the microsphere that is trapped in there. So this is for future sort of work. So we can actually go back and at least just for fun extract some physics from this and say, okay, so we've used, actually we've done this with 3 spheres, actually in both the old trap and the new trap with different voltages and along different axes. So you see the excitation of the for the measurement is done for microsphere 1 is along X, then along Y and along Z for the 3 different ones. This guy was done at 20 volt peak to peak. This is 200 volt peak to peak, and the frequency is different. So this is actually all very different data. Oh yeah, the old trap, you can see old trap versus new trap because the electrode separation was actually different. Of course, omega is different, and the data taking is also different. But this is now the charge sensitivity, which is entirely noise dominated. There's no bias anymore. There's no signal at all. And you can see it here. This is for one of this data. This is the chi-square. And you can see that this is the chi-square. This is 1 sigma from here to here. And you see that 0 is well within 1 sigma. So you are really in the statistical sort of regime for this. And you get limits for these mini charges, which are between few 10 to the minus 5 to few 10 to the minus 4. If you combine those together, all those 3 together, you get 3.3 10 to the minus 5 electron limit, and which can be easily improved. We think it's nice from the point of view of those kind of measurements, and this is the preprint number which came out today. Is actually interesting to actually plot this thing, the sensitivity to those mini charge particles as noise on one side, or noise sensitivity respect to our current trap, or our current measurement, which is this point here, versus the electric field strength. Because you see, you can do 2 things now. You can actually reduce the noise, and that will automatically give you better sensitivity. And you can increase the electric field to excite this thing, which also will give you better sensitivity. The electric field is easy to increase. We have some problem with the feed-through. This is kind of silly, but with a better feed-through, we can actually have much higher field. And so that's a simple fix in the system. And the noise has to do mainly with pointing noise of the laser, or the laser, which has to do mainly with the free space propagation in air, and air currents and microphonics and all this kind of stuff. So this is all going to be fixed in the near future. So both of those axes will improve. And just for fun, those measurements here those are essentially free quark searches. When people used to look for free quarks, they were looking for charge 1/3, so they had typically sensitivities of 10% of an electron. And so those are those measurements down here. The permanent dipole moment that we see is sort of somewhere represented by this line. And this measurement here is our very first paper using microspheres. That's actually the data I showed you at the beginning, the first slide that I showed you. And this is the paper that was a little bit better, but not much better, by David Moore's group, repeating that measurement essentially. And our current work is here, which you see, is not that much better, except this has no background really. You don't need to. So the difference between this paper here of ours is that here we just took the worst possible amount, background and called that the limit. Dave was a little bit more aggressive and claimed that he could cancel some of that. Here we don't cancel, we are slightly better, but we don't cancel anything. There's nothing to cancel. So we think that that actually somewhere we'll be able to somehow be somewhere in this region in the next year, because it should be pretty straightforward to actually, and this is going to be background free, as I just say. This line here, okay, is neutrality of matter line, and the argument goes as follows: if instead of thinking that in the microsphere I have one mini charge of 10 to the minus 5, I say that that charge of 10 to the minus 5 is equally distributed among all the atoms in there, and all the electrons and the protons. Now I'm measuring the difference in charge between electrons and protons. For that, there is a limit, which there's this PRA paper here. And that comes from a very clever experiment done actually by a friend of mine, Padova, which is also somewhat, to my opinion, dubious. It's very, very clever, but I'm not sure I completely believe the result. What they had, and it's actually nice to actually, describe it, because it's really actually very clever. So they have a sphere, which is filled at high pressure with some gas, I think sulfur hexafluoride, but I'm not sure. And then they have an electrode in the middle of the sphere, and they apply an alternating voltage between the center electrode and the surface of the sphere. And then they have a microphone listening. The idea being that if there is a small charge difference between electrons and protons, the entire gas would be sloshing around, and they would hear it with the microphone. I am not entirely convinced. I mean, they cannot calibrate this thing. So I'm not entirely convinced that if there was a signal, they would actually see it that way. But sure enough, they look at lots of gas, and so they actually have very good sensitivity. But I think we'll actually get there with microspheres, particularly after, we'll need to beat down the induced dipole moment, which we haven't really investigated much yet, but we know already how to do it with that B parameter. And that's actually a summary of the millicharge compared to other experiments in a different way. Here I'm just showing things in terms of the sensitivity in those two axes of sensitivity. Here, as it's more commonly done, I have charge sensitivity on the horizontal axis and abundance per nucleon on the vertical axis. And again, this is our very first old measurement, and this is the Yale measurement, Dave Moore's measurement to improve things a little bit. And the work here actually pushes the charge sensitivity just slightly further back. But now, since there's no background, you can be more confident and extrapolate back here, meaning you can just say, well, I've measured few 10 to the minus 5, but maybe this 10 to the minus 5 of a charge is distributed over the entire microsphere, all of the protons and electrons in the microsphere, and that will be when you go here, when the abundance becomes 1, that is, you get 1, pico charge or whatever, femto charge per nucleon, or per proton and per electron, and that will be sort of up here. And the result that I just described, the gas sloshing, is a point in this graph that is somewhere up here. Anyway, so we will improve, I think, all of those things soon, having learned how to deal with that chart, with that kind of system. And I think I'll close here, introducing the various people who have actually done all the measurements here. Thank you. And I don't know how I did at time. Okay, it was kind of longer than I thought, but all right.
Giorgio, thanks a lot. Do we have questions?
Kind of an obvious question. So, are you also going in the direction of investigating different particles for levitation?
Yeah, that's
this silica or
yeah, very good question. Yeah, so we've been saying we want to try we've been buying all sorts of strange materials, and then we never have time to actually do that measurement. It's always the measurement we'll do next when we run out of other things to do. The answer is yes, we should do this, and that's why we have this old trap, But then the old trap, we really like to run the kind of dipole thing both in the old trap and new trap to check whether there's any systematics and so on. So that took a few months, so that was used for a few months that way. Eventually we'll get there. We even have micro diamonds from some Swiss company making diamonds, and they just send a sample. So those are a little bit larger. They're more like 15 micron diameter. With 1064 nanometer laser and at least the Stober silica thing and so on, Dave Moore claims you cannot trap larger than 15 micron diameter. Actually, this goes back to something in Lorenzo. I don't remember. I was thinking about something about this when you during your talk yesterday. I don't remember how I connected this, but oh, somebody was asking sizes. For at least for this kind of silica and 1064 nanometer, there is a funny effect that if the microsphere is larger than 15 micron, the claim is, you start vaporizing. You know, there's so much power that it vaporizes until it becomes 15 micron, and then it becomes stable. But for other materials, maybe it's different. And we also have few silica microspheres, but those are really annoying because they're not very consistent in size. There is very broad spectrum of sizes. And so it's not, I don't know, I'm just worried that if you put this stuff in the trap, then something bad happens. You know, you just get, I don't know, dust everywhere. So we'll definitely try. But we even have barium, the thing which is very, that they make dielectric of capacitors, which is very polarizable. Barium, I forgot. Barium, say again?
Barium titanate?
Yes, barium titanate, yes. We have also barium titanate microspheres to try, yeah. I also at some point would like to try radioactive microspheres and actually see whether we can see the recoils from decays. It turns out it's not as bad as one thinks in terms of safety, because we do have, you know, from my other activity, we have actually a radon source, and so you can actually, if you levitate a plastic microsphere, which by the way we've never done, but you know, should be able to actually levitate a polystyrene sphere. Radon adsorbs like all noble gases, so you can actually put a little bit, a few torrs of radon in the vacuum chamber when the microsphere is trapped, and some of the radon will diffuse in the microsphere, then pump out everything, and then look at the alpha decays. I think that should be possible, and I'm very comfortable I can do it in the lab, and I can even tell health physics, and they will not get excited. Because that radon source is in the lab and it spews out radon all the time, and they know, and it's fine. So I mean, if you go in a mine, it's much worse than our source. So okay, but anyway, so there is a number of ideas to actually try some of those things, but we just never have time to do that. Anyway, yeah.
I have two questions. The first one is with the sloshing back and forth. Could you not just cover it with another shield?
Yeah, the answer is yes, but that in principle. But this is really tricky. There's already, imagine, this is like a micron away. The whatever shield is a micron away from the attractor because you want to be really close there, right? And so everything has to be parallel to everything else. So in principle, yes, you could bring in something else, but it's getting kind of really tricky. Incidentally, one of the trivial upgrades to the system is that the old suspension of the attractor was kinematically idiotic, the way we built it, because there are some tilt stages. There's the fast stage. You want to be on top, on top of everything because you don't want to load it with more mass of stuff you don't need. So that fast stage was on top, and then was mounted on a three angle, tilt, whatever, other stages which are to align it. But that means that when you align, when you align it this way, the thing does this, and it moves a lot horizontal. So aligning this thing was a real nightmare. Now we have rebuilt it, building our own, 3D printed metal, aluminum tilt stage on top. And so now it's on. So anyway, now the kinematics is better. So maybe, the alignment is going to be easy enough that we can try to add something else on top. to be honest with you, again, yesterday I learned, it occurs to me that we don't need to do imaging in X and Y in the light, with the light afterwards, but we can do it also from the reflected light. And that may solve everything. So that's that was, if that works, this was an extremely useful visit. Also because, to be honest with you, and maybe some of you has a good idea on this, or this is an academic question to some extent, but I never understood why our XY imaging system works reasonably well. Because what you see on that quadrant diode is essentially the shadow of the microsphere. And the quadrant diode, in principle, I mean, the kind of thing you'd like to see on the quadrant diode is a bright spot in the middle of the 4 quadrants. Now we have an anti-spot. We have a halo of light with missing light in the middle. And somehow the quadrant photodiode still understands, where this thing is. In principle, you could even, calculate how well this is supposed to work. We never did it because it just worked. And I actually had predicted it wouldn't work, because it seemed really bizarre, but then it works, and so. But maybe it doesn't really work very well, and if you use the reflected light, it will be much better. And so actually, yeah. So maybe you don't need to put a shield on top at all anyway. The other thing is that we are painting most things black. So the 6 electrodes are gold coated, and now we've learned how to actually spray Aquadag. You know what Aquadag is? It's actually some magic old-fashioned thing that no one uses anymore. It's some sort of colloidal graphite paint that they used to paint on cathode ray tubes, on the back of cathode ray tubes, and it's conductive. It's very reasonably conductive, and it's amazing because it's UHV compatible. I don't understand how it works. There are really flakes, small flakes of graphite, and they are suspended in some ammonia. You guys are laughing, so you know something about this. In some ammonia-smelling solvent, which I think is just water and ammonia. And it evaporates away, and there's nothing left. It's just the carbon. Why the carbon sticks, I think, is van der Waals forces. But it sticks really well. I mean, if you do it well, you can run your fingernail on it, and it doesn't come off. And if you do it stupidly, it doesn't work very well. Because what happens is that you make a droplet, the surface of the droplet evaporates, the water evaporates, and it becomes like a shell, and then there's still water underneath, and then it breaks, it flakes off, it's just a mess. But what you have to do, and I can actually give you a lecture on this because I spent lots of time figuring out how to do this. You actually get a spray gun and put the part you want to coat on a hot plate, so it's running at like 50 degrees C or something, and then you spray with the spray gun. That way, it dries immediately, and it doesn't in very thin coatings, and then you repeat the coatings a few times. So you get very black things. We actually sent some samples to LIGO. They have a way of characterizing the reflectivity of things, and they are essentially almost as good as their best material. That is this Akchar, whatever that thing is done in Israel, but ours is kind of essentially free. And you can do it yourself on all sorts of fun shapes and so on. So now all of the inner part of the trap is painted that way. But now the attractor you cannot do. I mean, I don't. If you start spraying, I mean, that thing, you just look at it and it breaks. So that will have to stay gold coated, I think. But anyway.
There's one more question about this 100 pixel sensor.
Yeah. No, it's silicon, actually. It's silicon, but the quantum efficiency is essentially, well, I don't want to say 100%, but I mean, it's very large. It's more than 50%. And the reason why that's the case is that it's very deep. It's like maybe 100 micron deep. And so you need a substantial bias. But it's convenient, it's silicon.
And it's something you can buy off the shelf?
No, but after we managed to make it work, I can send you some. And I say after because we have like 20 or 30, and I don't know how many will break. I mean, I just want to make sure we have, for our lab. Those are made by Slack for us as a favor, essentially. They make X-ray detectors for their X-ray stuff, and somehow we found that what we needed is almost identical to one of their processes in terms of process. And so on some wafers, they just put patterns for our things, and they just made them in the same run. So those are kind of very special proprietary, you know.
And for readout, do you really need all the different, do you need so many digitizers, or can it just multiplex them?
They're multiplex actually. So we have, well, they're multiplexed in clusters of, I don't remember, like 4, 6 or something. So there is a chip we found, a commercial chip that is preamp and multiplexer, and then you run them into an ADC. The reason we haven't done this yet is just pure manpower, kind of. You know, the person who's been doing all of the electric dipole moment stuff is Nadav, who's there to the left, and he was also the person developing the electronics. And so when this thing became more interesting, he dropped everything else and worked on the dipole, and so that was left behind. So at some point we'll do it, but it's just a matter of manpower.
So on the neutrality of matter plot, are there any astrophysical bounds on that?
Yeah, that is a good, I don't think, so the answer is, okay, first of all, that's an excellent question, right? I mean, if you, well, okay, so the answer is they're not as good as that, yeah, also, okay, they're not as good as this PRA thing here. I believe the reason is that space, you know, funny enough, I like to say it this way, interstellar space is very conductive, which doesn't seem like reasonable, but the thing is that if a planet, so if a planet is charged because there is an imbalance between electrons and protons, it will immediately suck electrons in, you know, from another object one way or the other and neutralize itself. So you usually those large, you know, on cosmic scales, right? You know, time scales, like, you know, in I don't know, a million years, there's been enough electron flow from one to the other, and then meteorites and so on, that electricity neutralizes everything. I think that's the reason why you don't have. Now, there might be more subtle things, like usually there's, many of those things come from some supernova stuff. Yeah, I don't know that, but I don't think it beats that because you know, if you look on the particle data book, the little thing, this is the limit that is usually given. Yeah.
So we do have still a couple of hours. Giorgio will have to leave around 3.
Yes.
I don't know if you checked out of the hotel already.
I checked out. I just have my suitcase to pick up
very
there.
good. So
with
that
my
means we have like 3.5 hours still to go. There are some labs that still need to be seen, and we also, of course, want to use the time to sit together.
Absolutely.
Yeah. Well, I guess who's next with the lab tours? What was the? Okay, so one of the two. The question is, Jakob will come at 12. So how should we do it then?
Maybe I start. No?
Okay, so then you start with Giorgio now. Well, then there will be a lunch break anyways. Yeah, we can grab lunch together also, and then for this afternoon. So Mario was able to book a dinner place tonight at
Ash?
yeah, right. Okay. Time?
At 6.
At 6 p.m. Okay, so that means we should start drinking now. Sorry for that.
Yeah.
But then people will talk more.
Yeah.
It certainly relax the atmosphere even more. Yeah, well, then we stick to 3-ish. Maybe 3:30. I need to see that I can wrap everything up by then. Pun not intended. And my schedule. Well, and we need someone to still get something to drink then. That would be great. Around to the young.
Yes, sorry.
Jason Hogan also wanted to do this kind of neutrality things with